Good morning, everyone. I am Dr. Sweety from the Department of Physics of University of South Africa, here to present here some of my research findings. Memristive behavior of undoped and doped polyvinyl alcohol, cadmium sulphide nanocomposites. The outline of my presentations: introduction, experimental, conclusion. Now, let me speak about the missing link. In case of the human evolution, we talk about the missing link. But here, what I am talking about is a missing link in case of electronics passive elements. In electronics, basically, we all know we have the three passive elements: resistor, capacitor, and inductor. But in the year 1971, an electrical engineer, Leon Chua, he found that there must be another element present apart from these three elements, passive elements, that we commonly know in our textbooks. And he said, there is a missing link here. And based on the relations between the resistor with current and voltage, capacitor on the charge and the voltage, inductor on the basis of the magnetic flux and the change in the current, he said that this missing element must have a linkage between the magnetic flux and the charge. And later on, he named it as Memristor. That is a memory with a resistor. So now, what is a Memristor? As I already told, that this is a memory with a resistor, and it has got a property that the resistance of the material can be memorized by the material. And M, as shown in the equation, is the memristor that gives the relation between the change in the magnetic flux with the change in the charge. And it was almost in a theoretical chapter for almost 40 years. But later on, in the year 2008, from the HP lab of California, Stanley Williams, he first practically found the practical memristor. And now the question comes, what is so important about the memristor? Memristor, at present era, we have the problem with the packing density of the transistors. And it is, according to Moore's law, it is said every 18 months the packing density is increased, is almost getting doubled. But when we go to the application of electronics, if the sizes becomes very less, then we have other problem with the power, dissipation of the currents, and so and so. To overcome this packing density problem, if we can use, instead of capacitors or transistors, if we can replace by memristor, this will be of much more advantage to us. And at present, the flash memory is almost of, we all know it's in a very less bytes, but it is said if we use memristor, it can go up to 100 terabytes in a coming year. So these are the advantages of using memristor. And showing here in the figure 2 is a relation between the current and the voltage. And here, as we can see in figure 4, for the same voltage application, we are getting two values of current. But in case of resistor, when we use, for the same voltage, we get same value of current. So from this particular figure, we can make out that it means for the same material at the same value, we have two resistive states. And when we come to the digital electronics, we know we have the value 1 and the 0 that represents high voltage and the low voltage. in case of digital electronics, and that we say it's bits. So suppose a bit may have 1 or 0 value. So this can be represented by these resistive states as is shown in figure 4. Now the possible applications of Memristor comes with non-volatile memory, crossbar latches as a transistor replacement. As I have already told, the advantages is the packing density. We can have a higher packing density in this case. Then programmable logic and signal processing. This is where we can replace the logic gates, that is AND gate, NAND gates, we can replace only by using the Memristor. Memristor is not that it only is seen in nanoscale. It can be also seen in case of thin films and many more. But in nanoscale, the advantage is that it automatically, naturally comes up. Because in nanoscale, when the electronic and the ionic transport are coupled with under external bias, then we see this memristive characteristics. So based on this idea that when it can be so prominent in the nanoscale, we have, and it has been already reported in CDSE, ZNO, lead sulfide. Of course, that was my own work. These things has already been reported. And we now come to next, that is CDS. Now, the question may be why I'm again going for CDS. Memristive characteristics may vary from material to material, and the variation in the resistive states, the difference in the resistive states may vary from material to material. Now, the importance of the variation, that is ratio between the higher resistive state and the lower resistive state, must be always greater than 10 to the power 3 in case of memory application, so that there is no probability of misreading. In this case, in some of course, in PBS, we could find to be almost 10 to the power 2 to 10 to the power 3. In CDSE, they will have found to be 10 to the power 3. So after going through this, we have decided to take cadmium sulphide. Although I know this cadmium sulphide, I have seen in last few sessions, it seemed to be very toxic. It's already known. But still, we are using this because this is a very common material that we are using in electronics for using manufacturing of photoresistors, LEDs, solar cells, and laser diodes. And mainly as a nanocomposites, we have this one advantage of tunability. If we go for changing the sizes of the cadmium sulphide in a quantum dot structure, then we have a tunability in the absorption spectra. So we have taken cadmium sulphide. Next, we have used polyvinyl alcohol. Polyvinyl alcohol is also non-toxic. This seems to be good, but it has got some advantages for being non-corrosive, and it's almost, we get uniform distributions of the quantum dots, and it is optical and photochemical stability. So for all these good things, we have taken polyvinyl alcohol as the matrix. So the experimental stages consisted of 3 phases. First was the synthesis of the nanocrystals, characterizations. This was done mainly to confirm the nanoformations of the samples. And the third was to study the memristive behavior. So coming to the synthesis state, this is a very simple chemical route method that we have adopted. And the precursors we used were the cadmium chloride with sodium sulphide. And as a matrix, we have used polyvinyl alcohol. And as anti solutions, after forming by using a simple magnetic stirrer at a particular temperature and in a particular speed, we could get that cadmium sulphide nanocrystals embedded on polyvinyl alcohol matrix. Second was we even went for doping of the cadmium sulphide nanocomposites with copper, and for that we have used precursors copper chloride, sodium sulphide, cadmium chloride, and along with the polyvinyl alcohol as a matrix, and also at the same time so that it works as a capping agent. So this is a simple fabrication way for nanocrystals. So now next procedure was the characterizations. This is the X-ray diffraction pattern. This X-ray diffraction pattern, we could see the peaks that can be seen here corresponds to the JCP-DS curve that shows that the CDS has got the cubic structure. And we could also see prominent peaks due to the polyvinyl alcohol matrix. And by using the well-known Debye-Saros formula, we have found that the sizes of the samples comes in the nanometer range, varying from 3 nanometer to 3.89 nanometer. And the variations of the sizes in the samples can be due to, are generally due to the temperature variations and the stirring speed variations in the fabricating process. The second characterization of UV visible spectroscopy. Here we see the absorption edge for bulk cadmium sulphide is almost 500 nanometer. But here in this case, we could see the absorption has shifted to the lower wavelength, and from this way, and there's a variation in the band gap of the samples. Generally, in case of bulk cadmium sulphide, the band gap is 2.42 electron volt. But here we have seen the variations in the band gap of all the samples. And the largest variation in case of the copper doped sample, that is with 3 electron volt. The third characterization was photoluminescence, and here we could see the peaks, prominent peaks that corresponds to the native atom. And apart from this, we could see the bandage emission for the doped sample at 414. And also we could see for the trapped emissions. So from this particular characterization, we can see that the doping has got significant effect in case of the samples that we are using. This is the transmission electron microscopy image for the copper doped cadmium sulphide samples. And from this, we can find that the sizes of the samples are in nanometer range. So after these characterizations, we could see all the samples that we synthesize in the nanometer range. They are showing the quantum confinement, and of course, the presence of the dopant are showing significant variations in the characteristics. Now, there may be a question why we are using the dopants. When we go for memory applications, to have the retentivity, to increase the retentivity, we need to use dopant, so that we can retain the we can retain the information for a longer time. Now next is the device fabrications. This was this very simple way by spin coating the sample on a glass slide. We used silver electrodes or silver pastes, and based on this was of course this films were in the nanometer size, less than 100 nanometer. Then by using the CV Kittlemeter, we could get the IV characterizations for the samples. This was done in the lab. Here, as we can see, with the same voltage, we are getting two states, resistive states, and corresponding to that, the variations in the current. And on the left side is a log plot. And here we can see the variations in the R-off to the R-on. And that shows that the sample has got a potential for applications in memory. Because in case, if we would have used a resistive sample, for the same voltage, if you whether going to forward way or in the reverse way, we'd have got the same value of current. But when in case of this sample, we can see for the same voltage, we are getting two value of the current. So we can say there are two resistive states. That's one of the lower resistive state and one is the higher resistive states. Now coming to the next this is the doped sample. This is doped with copper. Here too we could see there's a good variations in the resistive states, both in the forward bias and the reverse bias, but some variations in the reverse biasing we can see. This may be due to the trapping of the charges. And this is another sample that was a bit lightly doped. Here we can also see, but here we have observed that if we calculate, then we see that the R-off to the R-on states have reduced comparative to the undoped samples. The similar findings has been also reported by other workers in case of Giordano electrochemical devices, even in case of the CDSA devices. So after being encouraged by the result, the second step was that we have fabricated a device with the ITO-coated glass slides, spin-coated on that the samples of cadmium sulphide, and that on the vacuum deposition process, we have even deposited the aluminum as an electrode. Then by using the CV Kitli-meter, we took the IV characterizations of the samples. And here we have seen the R-off to R-on ratio is better, and we repeated the same cycles again and again, moving from the forward biasing, less voltage to higher voltage, then from higher voltage to this 0 voltage, again the reverse way. And we have seen that for this, we get multiple cycles if we go on repeating. And this denotes that this one cycle represents 1 bit. And the second cycle, the first loop, is for the 1 bit. Second loop, that's pink color, that's for the second bit. For the 1 bit, we have 2 resistive states, the 0 and the 1. And similarly, for the second bit also, we have the 2 resistive states, 0 and 1. And even for reverse bias, we get the same characteristics. But when we go for the copper-doped samples, we have the same character. We have the R-off and R-on in both the sides, but we could see there is an asymmetry in forward and the reverse directions. This can be because here we are using electrodes of one having an OMIC contact and another having the Schottky contact. So for that, maybe we are having the difference in the characteristics in the forward and the reverse directions. So from these findings, we have concluded the nanocrystals of cadmium sulphide and copper-doped cadmium sulphide was successfully synthesized by adopting chemical route method. This is a very simple method. Then characterizations were done, and we could see there's successful formations of nanosamples. And by using the device that is made of silver and ITO, that's made of silver electrodes, and also with I2 and aluminum as the electrons that exhibits Memristive natures. And we could see that introduction of the dopant has got significant effect on the Memristive natures in the devices. And from this, we can conclude that this particular sample has got the potential for application as a non-volatile memory. Thank you. Thank you.